Yes, thank you very much, Alexander. Um, and I'm also very happy to be back at the ILP conference. I think in about 29 of the 30 conferences, I've never had the pleasure of starting off the conference. So this is a new thing. So I hope not to make a mess of it. This is a summary of a paper that is joint work with Michael Bain and Angaraj Baskar here in BITS-Goa. It's about learning explanations for biological feedback. It's actually okay, so my screen is sort of frozen over. It's actually an attempt to formalize and use some remarkable work by a famous Belgian mathematical biologist, Renee Thomas, who spent almost 40 or 45 years looking at logical ways of representing biological feedback. Most of that work is in this really amazing book, which I would recommend anybody interested in logical reasoning and its applications to biology to look at. So the main ideas in Thomas's work is that feedback loops are an essential part of regulation in biological systems. So to understand biological systems, you really have to understand feedback loops. And he proposed and consistently defended the position that logical descriptions are an appropriate representation for explaining biological feedback. And he went on to propose something called kinetic logic, which was developed specifically to act as an intermediate representation between the verbal descriptions that biologists use and differential equation models, specifically aimed at feedback in biological systems. So the summary of this work, just in case I run out of time as we speak. So kinetic logic is essentially a kind of asynchronous logic for representing and reasoning about feedback in biological systems. And in this paper, and to some sense, this talk, I won't be talking about the logical specifications for kinetic logic, which we provide in the paper. As far as we were aware, there was no such specification before. We then implemented that specification by extending the basic event calculus and then proposed some mechanisms for learning kinetic logic descriptions using inductive logic programming and abduction, and then applied that to some synthetic and real systems. So just to give you background, the basic feedback loops that we're interested in are either negative or positive feedback. I'll just talk about the negative one first. So the negative feedback, in this case, say, suppose there are two variables and an increase in X causes an increase in Y, and that in turn decreases X. So this forms a kind of negative feedback loop. So each individual interaction may be positive or negative, but then when you loop them together, you get a negative feedback loop. For more than two elements, an odd number of negative interactions in general results in a negative feedback loop. An example of this is homeostasis, where animals keep temperature constant, sort of like thermostat, which oscillates around a fixed temperature. So it's known that negative feedback is necessary for oscillatory behavior, not just in biological systems, but systems in general. So positive feedback loops, here there's an example with, say, two negative interactions. And for more than two elements, an even number of interactions results in a positive feedback loop. And an important area of biological functionality where positive feedback loops are seen are in cell differentiation, for example, in embryo growth. So positive feedback loops are necessary for multi-stationary behavior. So, different cells ending up as different specialized kind of cells. The kinetic logic basics, I won't, as I said, in 15 minutes, I really won't have time to go into all of the details of kinetic logic. The paper is long and a little bit involved, but most of the ideas are summarized here. So the basic idea for kinetic logic, the starting point, you could think of as a simple stock flow type of differential equation where the rate of change of an xi is dependent on something increasing it and something decreasing it dependent on its value, which to a first approximation in kinetic logic is taken as a sort of a function of a capital X, which is the function f of xi, which depends on all the variables and minus the value of the little xi itself. So this is very similar, for those of you who've seen it before, to a kind of bathtub model where there's an inflow, which is the capital X part of it, and there's an outflow, which depends on, say, the level of the bathtub, which is the xi, and the rate of change of the level in the tub depends on the difference between the in and the out. Now, kinetic logic, the basic representation is to identify this capital Xi, which is a function of all the other values of variables in the system. It's a logical function. It's a sort of synchronous logical function in the sense that it just depends on that time instance. And it represents usually some important or meaningful biological event. For example, if little xi is a protein, then capital Xi is a gene that encodes that protein, or a set of genes, for example. And the other representation choice that is made in kinetic logic is that the little xi and capital Xi are discrete value, either 0 or 1 for simple kinetic logic, or multi-valued for generalized kinetic logic. There's some explanation in Thomas's book about how to get to these values. Now, the dynamics of this logic are fairly straightforward in principle. So if this capital Xi minus little xi is greater than 0, then little xi, lowercase xi will increase. If it is less than 0, it will decrease. If they're the same, then nothing happens to xi, except there are some unless stories in the square brackets, which constitute at least 2 levels of exceptions that we were able to identify in Thomas's work, which sort of makes the dynamics a little bit more complicated than just these simple rules. So the event calculus, for those of you who are unaware of it, is a very simple kind of way of reasoning with time. You can either look at the table or the logic program on the right. It basically has 2 kinds of things in it: fluence and events, and of course time. Fluence are things that change with time, and events are things that happen. Fluence are initiated by some event happening at some time t, and are terminated by can be terminated by some event happening at some other time t. So in the meantime, a fluent either holds or doesn't hold. So a fluent holds if it is at time 0, if you're told that it is holding at time 0. Otherwise, it holds at some time t if some event happened which initiates it and nothing happened which terminates it. And that's it. I mean, that's about it for the event calculus. The rest of it is for us to do, to write what initiates means, what terminates means, and so on. So we had to change this a little bit. We had to change it because we have this notion of delays in kinetic logic. So you remember I told you that x positively influences y, and then y positively influences x. But actually that doesn't happen immediately. There's some time delay, after which y changes, and there's some time delay after which the feedback returns back to x. So this event calculus, we had to change to an event calculus with delays. And then we had to write the axioms for kinetic logic, which are these ones for initiates and terminates for kinetic logic in that event calculus with delays. And then there's the domain knowledge, which we're interested in about the system that we're actually modeling. So these additional bits, this event axioms for kinetic logic and domain knowledge in the event calculus literature are just called domain-specific axioms, but we're sort of distinguishing them slightly for clarity for us. So we make certain design choices in the event calculus. We say that variables like xi's are fluents, so something holds, which means that that value of xi holds. And then the logical functions are events that happen, so that we represent these by the functional term f of xi, which really stands for that capital F of xi. There's also a clock tick, which keeps happening every time instant. And we write these kinetic logic axioms, as I said, which involve some delay predicate, and it involves some happens, which in other words, some event happens. The P over here is pathways, biological pathways. So there are different biological pathways and behaviors along those pathways. The rest of it is slightly unimportant, but roughly this is what a kinetic logic axiom looks like in the event calculus with delays. So what is the learning story? Well, if you're given data of this kind, which is, what the value of x is, what the value of y is, what the fx and fy values are at each time instant, which translate to some logical facts, we want to learn. So the logical facts will be certain things are holding, which are those fluents, the x's and the y's. Certain things are happening, which are these events, which are the f of x's and the f of y's. Then the logical, the learning story, at the moment at least, is that we want to learn about these delay predicates, and we want to learn about these happens predicates. So the first part is learning about events, which is given. Sorry, there are some planes going overhead, so there's a bit of noise from my side. So there's possible interaction. There can be possible positive interactions or possible negative interactions, which is the only background knowledge that we are using for the domain. It doesn't say which variable could be positive or which variable could be negative. We just say these are the conditions under which there's a positive interaction or a negative interaction. So we're trying to learn happens rules, which says that in this case, for example, an f of x event happens if the value of x is something, and it is opposite to the value it has an opposite value to the value of x at some point. So this is a kind of negative interaction, and z has a positive interaction with x. So this is an example of a kind of rule that we would like to learn, or more generally that that y has a negative interaction and z has a positive interaction using these background predicates. So we learn these sorts of rules, and we show you how in the paper using ILP and data like these, holds and happens and that sort of thing. So that's my alarm going off saying that I'm almost supposed to finish. But then the next part, so I'll request a couple of more minutes. Next part is learning delays. So we need to know also about these sorts of things, which we have to learn, which to allow us to use those event calculus axioms. So we would like to learn patterns like this, that, x, for increasing x by a unit, the delay is 1 time unit. For decreasing x by a unit, it's 2 time units, and so on, given the data that we have. And we do this using abduction. So we learn all these delay predicates given the same data, but we learn that at the same time as the happens predicates. So in principle, we have delays, we have happens from the data. So we should be able to use these event calculus axioms. But as I said, there's that bit on the unless part. So the unless part is that sometimes triggering events get canceled because of, say, a gene being turned off for some other reason. This can be inferred once you have the delays in the kinetic logic. But even if it doesn't get canceled, it can still not cause a change in the variable because two things happen at the same time and one overrides the other. And this part we have to learn from the data. So we would like to learn patterns like, overrides, predicates, which we again do using abduction. So now at the end of all this, you get a long set of clauses like this, some happens predicates, some delays. All these are actually really the output of some ILP program. But this is not really what a biologist wants. We actually extract explanations automatically from these in form of these kind of influence or interaction graphs. The -2, +3, and all this are actually, this is not 0 or 1 predicates. So these are multi-valued predicates, which says that there's the +3 means at the level of, if CRO is at the level of 3, and there's a positive self loop from CRO to CRO and so on. And we obtained these by post-processing the logical definitions by the ILP engine. We've done a bunch of experiments with synthetic models of various kinds of typical loops that are there in Thomas's book. We also looked at some obviously topical real systems for which there's some actual biological data. One with virus infection and how the loops that are involved when a virus invades a host, and the other one to do with an immune response when the host responds to the virus infection. So details can be found in the paper. Here are some examples of the actual models and the models that we find using this combination of ILP and abduction. You'll see that the models aren't perfect, but they do capture quite a lot of the real model. And although these may seem like only small models, but they're actually quite intricate in the fact that they all involve a lot of different feedback loops at various different time delays. So so the whole process can be quite complicated. So we get all the synthetic models, right? With the real models, there's very small amounts of data in the literature, 5 or 6 pathways, that sort of thing, and we get most of that right, but some of it is still spurious. So that's it. I mean, thank you very much for allowing me the extra time. These are the people whom I have to thank, all institutions and people. Thank you.